One day the stars will die and the universe will be left in a cold, endless night. Imagine every campfire in the world slowly guttering out until the last glowing ember is gone, except this takes longer than any human story, and there's no flashlight that can save you. In the next few minutes you'll get a simple picture of how that darkness comes to be, why it isn't just dramatic poetry, and what it means for everything that exists now. First we'll use plain examples, like streetlights going off one by one, batteries running flat, and embers cooling, so the giant timescales make sense without a math degree. Stick around and you'll walk away with a clearer, oddly comforting view of the universe's far future, plus a few surprising facts that make eternity feel a little less abstract. Defining eternal darkness. Physically, it describes a state in which the universe is so thinly lit and so spread out that starlight becomes a rare visitor and most places are dominated by cold emptiness. Small sources of light would be like lone porch lamps on an endless street. They exist, but the distances between them are vast and getting larger. Energy that once powered stars and galaxies has been smeared out so evenly that there are no big flows left to do work. Simple example. When a hot cup of tea cools to match room temperature, it no longer powers steam or movement, that same idea on a cosmic scale. The causes are straightforward in everyday language. Stars are powered by fuel, and when that fuel is used up the stars either die quietly or explode and leave behind dim remnants. At the same time, the space between cosmic objects grows, stretching light and thinning out energy. There are also objects like black holes that can hang on to matter for a long time, but even they are not forever. They lose a tiny bit of energy over extremely long periods and eventually fade. Think of the universe as a crowded party where slowly everyone drifts toward the exits and the music winds down until only a few people remain whispering in the corner. You can picture the sensory experience with simple comparisons. Standing under a clear dark sky in the countryside is the mild version. No street lamps, a sky full of stars. Now imagine those stars are mostly gone and the sky is a deeper, quieter black, with the occasional faint glow that takes a very long time to reach you. Life on a planet in that environment would feel like living during a perpetual long winter with very few warmth sources. Practical example, a rural home running out of electricity. You can light a candle, boil water on a camping stove, but the big conveniences and machines that made life easy have shut down. The deeper point is about available energy gradients, differences in temperature, pressure, or light that living systems and machines use to do things. When those differences fade, systems can't extract useful work anymore. A battery that is completely discharged is a simple household example. It's still there, but it won't power anything until recharged. In a universe slipping toward eternal darkness, recharging opportunities become vanishingly rare. Small, isolated pockets of activity might persist near rare energy sources, much like insects clustering around a streetlight after a blackout, but they are exceptions rather than a sustainable norm. Finally, the idea is less a dramatic scene from a movie and more a description of a final, very quiet phase under current scientific thinking. It sets a limit on how much large-scale activity the cosmos can support when energy sources are exhausted or too diffuse to be useful. That makes the phrase both poetic and practical. Poetic because of the stark image of a dark, sleeping sky, practical because it points to the simple rule that life, machines, and motion all need accessible energy, and without it, things go still. A little grim, maybe, but at least the silence would be excellent for starless stargazing. A brief cosmic timeline. In the earliest moments the cosmos was a seething, glowing soup where light and matter were tightly mixed, and conditions were far too energetic for atoms to hold together. As the universe expanded and cooled, those energetic particles slowed down enough to combine into simple atoms like hydrogen and helium, which then acted like building blocks for everything that followed. Think of it like steam condensing into droplets. When things calm down, structure can form. This cooling allowed gravity to gather slight clumps of matter into larger clumps, and those clumps were the seeds of the first stars and galaxies. Clouds of gas collapsed under their own gravity to make the first stars, and those stars acted like enormous, long-burning furnaces, fusing light elements into heavier ones. The process is similar to a kitchen stove where simple ingredients get transformed into a more complex dish. Hydrogen gets cooked into helium, and in massive stars the cooking goes further to make elements like carbon, oxygen, and iron. When the biggest stars ran out of fuel, they exploded in spectacular fashion, flinging these new elements into space where they mixed with other gas and dust. That recycled material became the raw stuff for planets, comets, and eventually life-bearing worlds. One everyday example: the iron in a kitchen knife and the calcium in bones were forged inside ancient stars. Planets formed from disks of leftover dust and gas swirling around young stars, clumping together like crumbs sticking into a snowball or flour gathering into a dough. Some of those planets stayed small and frozen, while others collected thick atmospheres and became the kinds of worlds where chemistry can get interesting. In systems with stable energy from a star, conditions can persist long enough for complicated molecules, and sometimes life, to develop. Our own planet is a practical example of how stellar materials and a gentle, steady energy source can create a remarkably busy chemistry lab. Stars don't live forever, their endings depend on mass. Small, sun-like stars shed their outer layers and leave behind dim, dense cores known as white dwarfs, like embers cooling after a campfire. Much heavier stars end in dramatic blasts that leave neutron stars or black holes, which are the dense, compact leftovers of those explosions. Over vast stretches of time, the formation of new stars slows because the available gas gets locked up in stars or blown away. The universe gradually drifts toward an era dominated by faint stellar remnants, cold brown dwarfs, and scattered particles, making the night sky much less bright than it once was. Even black holes, which seem impossibly permanent, are predicted to change very slowly by leaking energy in a subtle way described by quantum processes. This is a tiny, almost comical drip over mind-boggling spans that would eventually rob them of mass. When most energetic sources have faded and remnants cool, the cosmos becomes a realm where only low-energy light, rare particles, and an occasional faint flash from a dying object remain. Picture a party after everyone's left, a few embers, an empty punch bowl, and someone slowly turning off the lights. In that deep future darkness, the universe keeps expanding and thinning, and the grand, bright chapter of active star formation quietly closes. The Golden Age of Stars. When galaxies were brimming with cold gas, star factories worked overtime. Vast clouds of hydrogen and helium, simple gases that float through space, collapsed under their own gravity and lit up as new stars, like campfires sparked from piles of dry wood. Some regions were quiet, forming small, steady stars that stick around for a very long time. Other places were bonfires, producing many massive, bright stars that burned furiously and ended their lives in spectacular explosions. Big stars burn fast. Small stars pace themselves. Inside those stellar furnaces, light elements fuse together into heavier ones, a bit like heating sugar until it caramelizes into something new. Carbon, oxygen, iron and other building blocks of planets and life were cooked up this way and then scattered when massive stars died. A supernova throws those ingredients out like a pot of soup tipped over into a garden, and the next generation of stars and planets grow from that richer material. Think of it as cosmic recycling. Kitchen scraps become a better compost for the next crop. The high rate of star birth changed the look of many galaxies. They glowed brightly in visible light and in the glow of heated gas and dust, appearing as busy, colorful cities when astronomers point their telescopes. Collisions and close encounters between galaxies funneled gas into the centers and triggered even more making of stars, like a traffic jam that somehow boosts productivity. These bursts of activity filled space with energetic particles and light, and they also created conditions where planets could form from leftover dust and rocks. Studying that era helps explain why planets like ours contain the elements needed for rocks, water and life. Observations today catch hints of those busy periods by measuring specific colors of light from gas and dust, similar to noticing neon signs in a distant town. The work connects what we see in laboratories and kitchens, mixing ingredients, applying heat, and waiting, to the grand processes that built the raw materials around us. And yes, the universe had its own version of a bustling bakery, lots of hot ovens, a cloud of flour in the air, and a few incredibly dramatic cake explosions. Why stars go out? Stars shine by fusing light elements in their cores, producing energy that pours outward as light and heat. This fusion is like a steady engine, hydrogen atoms join to make helium, and the leftover energy pushes outward against gravity. When that fuel runs low, the engine slows, and the balance between outward pressure and inward pull changes. Think of it as a pot on the stove whose flame gets turned down until the bubbling stops. Smaller stars, like our Sun, exhaust their central fuel more gently. Their outer layers puff up and cool, becoming large and reddish for a while, and then those layers drift away into space. What remains is a dense, hot core called a white dwarf, essentially a glowing ember that no longer has fusion in its heart. It will slowly cool and fade over unimaginably long times, like the dimming heat from a fireplace log after everyone has gone home. Very massive stars follow a more dramatic route. Their cores keep stacking heavier elements until fusion no longer produces enough outward pressure, and the core collapses suddenly. That collapse can trigger a violent explosion that shines brighter than the whole host galaxy for a short time. This is what people call a supernova, and it can fling heavy elements into space. The leftover can be an ultra-compact neutron star, so dense a teaspoon would weigh like a mountain, or a black hole, a region where gravity is so strong even light cannot escape. The supernova is like a firework finale that not only ends the show but seeds the surroundings with the materials for new stars, planets, and even life. Stars can also go out because of outside interactions. In pairs, one star can steal gas from its neighbor and either reignite bursts of fusion or blow off layers in violent flashes. Some small failed stars never sustain steady fusion and quietly cool without ever shining brightly. These varied endings matter. The elements humans and planets are made of were forged in stars and dispersed when those stars died. It's poetic, and a little funny when you think about it. The atoms in your phone and in your coffee were once part of a stellar drama no less dramatic than a soap opera, just with far better special effects. Stellar corpses, white dwarfs to black holes. Stars end their lives in different ways depending mostly on how much material they packed in when they were young. Small to medium stars, those that never got hugely heavy, shed their outer layers in graceful clouds and leave behind a dense core called a white dwarf. Picture squeezing something the size of the Sun down to roughly the volume of Earth, that is a white dwarf, very compact and very hot at first, then slowly cooling. The force that keeps a white dwarf from collapsing further is a kind of pressure from tightly packed electrons. It's not magic, just very stubborn particles saying, no more squishing. Think of it like overstuffing a suitcase until the zipper fights back. The expelled outer shells often glow for a while, forming a pretty shell of gas known as a planetary nebula. No planets involved, just an astronomical misnomer. A useful everyday image is peeling an orange. The peel floats away while the fruit remains. Short, bright, and kind of photogenic. Over a very long time a white dwarf will fade and chill. In everyday terms it's like a hot coal that slowly cools to embers, though on cosmic timescales. Our own star is one of those that will follow this quiet path, becoming a white dwarf after it runs out of fuel. Stars much heftier than the Sun can go out with a far noisier bang. When a heavyweight star exhausts its fuel, gravity can overwhelm the resisting pressures and the core can slam together in a crushing collapse. The result can be a neutron star, a city-sized sphere so dense that protons and electrons have been smushed into neutrons. Short and extreme. A spoonful of that stuff would outweigh a mountain, which makes the idea of stubbing your toe on one rather unlikely but entertaining to imagine. Many neutron stars spin rapidly and send beams of radiation out like lighthouse flashes. Astronomers call those pulsars, so they act like cosmic metronomes that keep extraordinarily steady time. If the collapsing core is heavy enough, nothing can stop the fall and a black hole forms. This is not a literal hole in space but a region where gravity is so strong that not even light can escape from within a boundary called the event horizon. A clear everyday analogy is a drain in water. Things swirl closer and cross a line of no return, though space doesn't have plumbers. Matter falling toward a black hole usually forms a hot, glowing disk first, and sometimes violent jets shoot away along the poles. These accretion disks can outshine entire star clusters while they feed the hidden beast at the center. Different stellar corpses play different roles in the universe. White dwarfs can trigger spectacular explosions if they gain too much mass from a companion star, and neutron-star collisions fling heavy elements like gold and platinum into space. Black holes, meanwhile, sculpt their neighborhoods with gravity and light, influencing how stars and gas move in galaxies. In short, the afterlives of stars, from compact embers to spinning neutron lighthouses to gravity wells, are dramatic, varied, and crucial for making the galaxies, planets, and elements we see around us. A little grim, perhaps, but also how the universe does recycling on a grand scale. The decline of chemistry and life-friendly environments. Life depends on a set of chemical ingredients and a steady balance between them. Take away the balance and cells stop doing what they do. Carbon, hydrogen, oxygen, nitrogen, phosphorus and sulfur are core ingredients. Plants and animals need them to build tissues and run their tiny factories. If nitrogen and phosphorus are missing from soil, crops grow poorly and leaves yellow. That is why gardeners and farmers add fertilizer. The same basic need shows up inside your body. Iron in blood carries oxygen, and without enough iron you get tired, plain and simple. Chemistry can decline when those ingredients are taken out of circulation or locked away where living things cannot reach them. Rocks can trap phosphorus, soils can lose nitrogen after heavy rains wash it away, and oxygen can be used up when microbes break down organic matter, leaving water that fish cannot breathe in. A backyard pond is a good example. Add too much fertilizer to the lawn and runoff can spur algae growth. When the algae die, bacteria eat them and use up the oxygen, turning a lively pond into a smelly quiet soup where fish flop. Oxidation is another everyday process. When iron rusts it is still iron, but it's not useful in the same way. In nature, similar chemical changes can render useful molecules inert for life. The energy that drives chemistry is just as important as the ingredients. Life often uses differences in chemical concentration or heat. Think of a river flowing down a hill. Life taps the flow the same way a waterwheel does. At deep-sea vents, microbes harvest chemical energy from hot fluids. If that supply weakens, the whole local community collapses. Extreme cold slows chemistry like a fridge slowing bread going bad, while extreme heat can tear molecules apart, more like leaving an egg on a hot pan. Both ends of the scale make it hard for the simple reactions of life to continue. Everyday human experience shows how fragile these balances are, and also how we can help. Composting returns nutrients to soil, keeping phosphorus and nitrogen cycling where plants can use them. Aquarium keepers know to add aeration and change water to prevent oxygen crashes, and farmers use lime to counter overly acidic soils so plants can access minerals. Small actions matter. Protecting wetlands and reducing pollution keeps coastal waters from tipping into oxygen-poor, dead zones, and preserving vegetation helps maintain the steady flows of chemicals that ecosystems rely on. A little attention goes a long way. Plants don't have thumbs, so they can't call a plumber when their chemistry goes wrong. The degenerate era, faint embers of matter. Most of the light in this era comes from remnants that are slowly cooling, not from bright, new stars. White dwarfs, the dense cores left behind when medium-sized stars shed their outer layers, still glow like embers in a dying campfire. They shine because they were heated up during earlier stellar life and slowly release that heat over a very long time. Brown dwarfs, which never really ignited into full stars, lurk as faintly warm objects. Think of them like long-forgotten baking trays that still give off a little heat long after you took them out of the oven. Neutron stars and black holes remain too, compact and silent, often isolated and only occasionally announcing themselves when something wanders too close. The physics that holds white dwarfs and neutron stars together is a bit like a crowded elevator resisting more riders. In those collapsed objects, particles are packed so tightly that quantum mechanics, basically rules about how tiny particles behave, prevents them from being squeezed into the same state, and that creates a kind of pressure without needing heat. This degeneracy pressure is not the same as gas pressure in a balloon. It doesn't come from motion or temperature but from the particle's refusal to be crammed closer. So a white dwarf can be small and incredibly dense, but it won't collapse under its own weight unless something pushes it past a certain limit, in which case more exotic collapse can occur. With star formation almost halted because the available gas is sparse and spread thin across an expanding universe, the landscape becomes quiet and sparse. Collisions between leftover objects or rare accretion events, when material falls onto a compact object, can produce brief flares of light, like the occasional spark when you stir a dying barbecue. Planets and asteroids, stripped and battered, may slowly grind into dust through slow impacts and tidal forces, creating faint debris disks that glow weakly in infrared. Life on a planet, if any survived, would face a dim environment. Daytime would be feeble and nights long and cold, with energy sources limited to residual heat and occasional cosmic fireworks. Black holes, though invisible themselves, continue to play a role by swallowing nearby matter and by slowly losing mass through a subtle quantum process predicted by current physics, causing them to fade over extremely long timescales. Whether protons themselves eventually decay is unknown. If they do, ordinary matter could slowly dissolve into radiation and lighter particles, accelerating the thinning out of solid structures. For now, observations of white dwarfs and brown dwarfs in our own galaxy give scientists practical data about cooling rates and composition, helping them model how these faint embers behave when the stellar chorus has long since ended. Everyday analogies help. A white dwarf is like the glowing coal after a bonfire, dim but still radiating heat. A brown dwarf resembles a warm stone you left in the sun, not hot enough to be dramatic, but undeniably warm. Scientists use telescopes that detect faint infrared and optical light to study these objects, and computer models to track how they cool and interact. Humor aside, the degenerate era is a slow, patient phase of the universe where the drama of star birth gives way to the quiet endurance of compact objects and the faint, persistent afterglow of matter that refuses to disappear quickly. The rise of black hole dominance. Galaxies often host extremely massive black holes at their cores that steer the motions of nearby stars and gas. These central objects can weigh millions to billions of times the mass of our Sun, and their gravity is so strong that stars close to them move in tight, fast orbits that betray the presence of something compact and heavy. Astronomers watch those stellar dances and bright light from hot gas to know a black hole is at work, since the black hole itself gives off no light directly. Growth happens in a few familiar ways. One is feeding. Gas and dust fall in and form a spinning, flattened disk that gets hotter and hotter as it spirals inward, glowing in visible light and tenth rays. This bright, hungry phase can make the center of a galaxy outshine all its stars, like replacing a string of porch lights with a searchlight. Another is collision and merger. Whole galaxies can collide, their central black holes eventually sinking toward each other and joining into a larger one, much like two people drifting to the center of a crowded room and ending up standing together. Smaller objects, loose stars or clouds, can be pulled apart when they get too close, giving a sudden bright flare as their material is ripped apart and swallowed. This is called a tidal disruption and behaves like dropping a grape into a blender, but far less tasty. Energy released during feeding is a big reason black holes gain influence beyond their immediate gravity. Powerful jets and radiation driven by the spinning disk and magnetic fields can blast away or heat surrounding gas, stopping that gas from cooling and forming new stars. In practical terms, a single active black hole can act like a radiator that keeps its neighborhood too hot for baby stars to form, so entire regions of a galaxy grow quiet. Observations of active galactic nuclei and jets show how that feedback works, and the physics behind it is simpler than it sounds. Moving, charged gas plus strong magnetic fields equals focused outflows that punch through a galaxy. Mergers of black holes also reshape things in ways you can sense indirectly. When two black holes collide, they send out ripples in space, gravitational waves, that travel across the universe. Those ripples have been measured directly, proving that such mergers are real and sometimes dramatic. Over time, repeated mergers and steady feeding shift mass toward the centers of galaxies and clusters, concentrating gravitational power there, which then sculpts star orbits and the distribution of gas. And while tiny effects like Hawking radiation are a theoretical way black holes might eventually lose mass, for the supermassive ones we see now that process is vanishingly small. In other words, they're not going to fade away anytime soon, so don't expect them to tidy up the cosmic living room. Everyday analogies help keep the picture clear. Think of a black hole as a very heavy celebrity at a party. People, stars and gas, drift toward them. Security, gravity and dynamical friction, keeps them centered, and the celebrity's entourage and flashbulbs, radiation and jets, change how the rest of the party behaves. It's a goofy image, but useful, because black holes don't just sit there. By eating, merging, and stirring their surroundings, they grow into dominant players that control how galaxies light up or go quiet, and they help determine the cosmic landscape on large scales. Hawking radiation and black hole evaporation. Quantum effects near the edge of a black hole make it behave like a very faint light bulb, slowly leaking energy into space. Tiny pairs of particles pop into and out of existence all the time in empty space. When this happens right at the black hole's boundary, one partner can fall in while the other escapes, and that escaping partner shows up as a faint radiation. Think of those particle pairs as mischievous twins. Usually they recombine instantly, but the black hole can separate them and one of the twins runs off carrying away a bit of energy. That escaping glow acts like heat. The black hole has a temperature that sets the color of the light it gives off. In the same sense, a hot stove glows red while a warm cup of coffee does not. Smaller black holes are hotter and therefore shine more brightly per unit mass, while very massive ones are extremely cold and barely emit anything at all. In practice, this means ordinary, large black holes are effectively colder than the leftover glow of the universe, so they tend to gain a little material by absorbing background radiation instead of losing it. As the black hole loses energy through this radiation, it also loses mass, and that slow slimming down is what people call evaporation. The process is glacial for the kinds of black holes we know about. For those, the leakage is so faint that nothing noticeable happens on any human timescale. But as mass falls away, the black hole heats up, the leakage grows faster, and the shrinking accelerates, so it's a runaway effect once a hole becomes small enough. Picture a melting snowball. At first it barely changes, then as it gets smaller it melts quicker, and before you know it the last dribble goes fast. This idea brings up another puzzle that sounds like a detective story. If all that falls into a black hole is later returned as featureless radiation, what happened to the detailed information about the original stuff? Scientists debate whether the information is encoded in the outgoing glow in a very scrambled way, hidden until the very end, or stored in some other form. It's a bit like trying to reconstruct a finished cake from the crumbs and steam, maybe possible, maybe not, and the discussion gets lively. Detecting this radiation directly from astrophysical black holes is essentially out of reach with current technology, so researchers sometimes build tabletop analogs using fluids, light pulses, or ultra-cold atoms that mimic the same physics and have produced similar signals. Those lab results help test the basic ideas without needing a cosmic-sized black hole in your backyard. And while the whole picture mixes deep concepts in a way that can sound mysterious, the simple takeaway is this: black holes are not perfectly black, quantum effects let them leak energy slowly, and that tiny leak, over immense times, can lead to their disappearance, like a candle burning down until only a wisp of smoke remains. The black hole era, slow unwinding. When ordinary stars have faded and the night sky is no longer lit by starlight, black holes remain as the main lumps of mass quietly shaping what happens next. They are not perfectly closed boxes. Thanks to a subtle quantum effect, they leak energy in the form of very faint radiation, a process usually called Hawking radiation, which you can think of as tiny particles sneaking away from the edge of the hole. Picture a sealed bag with a very slow hole in it. Air escapes so slowly you hardly notice, but over an extremely long time the bag does deflate. This leaking is what drives the slow unwinding of the era dominated by black holes. Smaller black holes lose mass faster than bigger ones, because the smaller the hole, the stronger the leak. A small black hole is sort of like a tiny ice cube in a warm room that melts quicker than a huge block of ice. Large, super-heavy black holes barely leak at all on everyday timescales. they are the cosmic equivalent of a massive boulder that refuses to roll. Because of that size difference, the population of black holes changes unevenly. Lightweight ones wink away sooner, while the heavyweights stick around for an unimaginably long stretch. Accretion, the act of swallowing leftover gas, dust, or other black holes, can temporarily slow down the unwinding by adding mass back in, but as the universe thins out there is very little to eat. Collisions between black holes will still occur when gravitational nudges send them together, and those mergers produce bursts of ripples in space that are brief and energetic, but they do not lastingly refill the dwindling supply of matter. Think of a few cars occasionally bumping in an otherwise empty parking lot, loud at the moment, then silence once more. Over time the quiet dominates again. What happens at the last moments of a black hole's life is not fully settled in physics. The standard picture says the hole will keep losing mass until it becomes tiny and then radiates away the rest in a final, extremely energetic burst. Yet at the very end the rules of gravity and quantum physics meet in ways we do not yet understand, and some researchers allow the possibility that a tiny remnant might be left behind. It is like watching someone eat a cookie. You can predict most of the process easily, but whether one last crumb stays on the plate is unclear. That uncertainty keeps the endgame of the slow unwinding an interesting problem, not a closed file. Throughout this era the universe grows colder and darker as radiation dims and matter is locked into compact objects, with entropy, a measure of disorder, steadily rising as things settle into fewer, simpler forms. Lifelike complexity is effectively gone. The space between black holes is a sparse, frozen emptiness where sparse particles drift for ages. For a human brain this is hard to picture, so use the coffee cup example. Left untouched, the coffee gets colder and the patterns in the foam smooth out until nothing lively remains. The black hole era's slow unwinding is the cosmic version of that quiet, patient cooling, carried out on a scale so vast it almost feels like a joke told in geologic whispers. Crossing into the dark era. As the most massive stars burn their final fuel and fade, the cosmos moves into a much quieter stage where bright, steady sources of light become rare. Gas that once fed new stars gets locked up in dead stellar remnants or expelled so thinly that it can't clump together again. In plain terms, there's simply less raw material around to make new suns. Smaller, long-lived stars keep glowing for an unimaginably long time, but they are dim compared with the brilliant giants and they can't replace the lost light quickly. Picture the difference between a stadium floodlight and a single candle across the field. Both give light, but the scale has changed. Energy becomes harder to gather and use, because it spreads out and cools. This is the same basic idea as a hot cup of coffee cooling to room temperature until you can't get warmth from it anymore. Space itself is stretching, and that makes radiation lose punch as its wavelengths get longer and weaker, like a radio signal fading as you drive away. A useful everyday image is a battery-powered toy. Fresh batteries make it run strong, but as the charge leaks away the toy slows, then stutters, and finally sits still. The universe doesn't shut off suddenly, it simply goes into low-power mode. Some large structures remain, though they too eventually quiet down. Galaxies that once formed new stars become collections of elderly stars and dense remnants, while black holes sit as the most efficient sink of mass and energy around. Physicists predict that black holes are not eternal. They should, according to current theory, lose energy extremely slowly through a process that leaks particles and radiation, much like a tiny, steady drip from a very full, very slow-leaking faucet. If that leakage happens as predicted, even those dark giants will fade in the far future, leaving behind an even emptier stage. The crossing into this dimmer phase is not a sudden curtain drop but a long dimming with occasional bright flashes. Collisions between dead stars, rare accretion events where gas falls into a black hole, or the sudden ignition of remaining fuel in a stellar ember can create brief fireworks against the backdrop of decline. Think of a town where power is being rationed. Most lights go out, but every now and then a generator kicks on and some streets brighten for a while. Those brief surges don't reverse the overall trend, but they make the late moments interesting. For any beings facing this change, the practical effects are clear: fewer accessible energy sources, greater isolation as galaxies recede from each other, and a need to conserve or find new ways to extract usefulness from faint leftovers. The broad picture, a slow, steady dimming driven by expanding space and the running down of accessible energy, is the part that physicists agree on, even though some details remain open questions. So, in short, the universe doesn't flip a switch, it settles into night mode, and the challenge becomes how to make the most of the last sparks. Heat death, maximum entropy explained. Energy in a closed system tends to spread out until it is evenly shared, and that spreading is what scientists call entropy. You can think of entropy as a measure of how much the available energy is smeared around, or how little is left in neat piles you can use. A steaming mug of coffee cooling to room temperature is a tiny, everyday example. Heat moves from the hot coffee into the cooler air until both are closer to the same warmth. Short and simple, energy evens out. Entropy rises when things mix and temperatures even out. For a practical example, pouring cream into coffee quickly makes a swirl, then a single color. The cream has mixed and you cannot easily separate it again without effort. Batteries offer another clear picture. A fresh battery stores energy in a useful form that powers a device, but a drained battery has the same amount of material but the energy is spread into useless forms like tiny vibrations, and the device won't run. Even a tidy room left alone will slowly get messy unless someone tidies it. Maintaining order takes energy, and letting things go raises entropy. A little humor helps. It's as if the universe prefers comfy pajamas to a stiff suit. Maximum entropy means energy is so evenly spread that nothing useful can be done with it. Engines, plants, and cells all need differences, hot next to cold, concentrated fuel next to empty space, to produce motion or life. If everything is the same everywhere, heat engines can't run, chemical reactions that power life grind to a halt, and batteries are eternally flat. Picture a party where snacks are not just gone but have been pulverized and sprinkled uniformly over the floor. Nobody can bite into a cookie, and yes, that is a very dull party. Not dramatic, just quietly inert. The idea that the universe could reach this maximum entropy, no useful energy state is what people refer to as the heat death picture, not a fiery end, but a slow decline into uniformity and quiet. Local pockets of low entropy, a living creature, a machine, a star, can still exist for a long time by using up resources and creating more disorder elsewhere. A refrigerator keeps things cold inside by dumping heat outside. Ultimately, without fresh gradients to tap into, those pockets fade too. So while the concept sounds bleak, it's also a clear bookkeeping rule: without differences to exploit, no work gets done. That's both a useful science lesson and a slightly melancholy cosmic joke. Dark energy and the ever-expanding cosmos. Astronomers have measured that the universe is not only expanding, but that the expansion is speeding up. That speeding up is attributed to something called dark energy, a label for whatever is causing space to push itself apart more quickly over time. Observations of distant exploding stars appearing dimmer than expected, along with patterns in the cosmic background light and the way galaxies cluster, all point toward this extra push. In simple terms, dark energy behaves like a gentle, persistent pressure in empty space that makes the cosmic fabric stretch faster and faster. Think of the universe like a loaf of raisin bread rising in the oven. As the dough expands, all the raisins move away from one another. If the oven suddenly turned up the heat so the dough rises faster over time, that's roughly how accelerated expansion behaves. Only the oven is the rules of physics and the raisins are galaxies. The analogy helps because you can picture how expansion affects distances even when the raisins themselves don't grow. One practical way scientists study this is by mapping where galaxies are and how fast they appear to recede, using light from particular bright explosions as distance markers. Those so-called standard candles behave predictably in brightness, letting researchers judge how far away they are and how fast the space between us and them has stretched. Large sky surveys and space telescopes collect this information, like cosmic census takers, compiling large catalogs that reveal the expansion history. It's a bit like watching a slow-motion movie of the universe getting slipperier and slipperier. There are several leading ideas about what dark energy might actually be. One straightforward idea treats it as a constant energy inherent to empty space, a kind of built-in tension of the vacuum. Another idea imagines a field that changes over time, more like a cosmic weather system than a fixed property. Neither explanation has been proven yet, and both raise tricky questions about why the effect has the strength we observe. For now, dark energy remains a working label while researchers test these possibilities with more precise measurements. The consequences are more than academic. The long-term cosmic picture depends on how this force behaves. If the push continues steadily, distant galaxies will move away so quickly that they will fade from view and local groups of galaxies will remain the main structures left to see. That sounds a bit bleak, but it also gives astronomers a clear set of predictions to check, a roadmap for future observations. Meanwhile, dark energy keeps being one of the biggest puzzles in physics, a mysterious ingredient that, despite its name, keeps the universe lively and oddly caffeinated. Proton decay and the vanishing of ordinary matter. Protons are the tiny positively charged particles tucked inside every atomic nucleus, and by every practical measure they act as if they will never quit, but some theories in physics suggest they might slowly fall apart over unimaginably long times. The idea is simple to state: a proton could transform into lighter particles, such as a positron, the electron's antimatter twin, and a pion, instead of staying forever locked inside an atom. In plain terms, that would be like a brick in a wall quietly turning into dust that spills away. The wall would still stand for a very long time, but the individual bricks would be leaving. Quarks, the even smaller bits that make up protons, would reorganize or escape, and the atom that depended on that proton would no longer be the same. Physicists hunt for such rare events by building enormous, quiet detectors deep underground and filling them with huge volumes of ultrapure water or other materials. A proton decay, if it happened inside one of those tanks, would produce fast-moving charged particles that flash faintly as they travel through the water. Sensitive light sensors around the tank can pick up that flash. No unambiguous proton decay has been seen so far, and those searches tell us something important. If protons do decay, their typical lifetime must be staggeringly long, at least on the order of 10-34 years for some of the most studied decay channels. So far, experimental evidence makes ordinary matter effectively stable for anything we, or a few billion generations of humans, would care about. Your coffee mug is safe for now. If proton decay does occur, the long-term consequences for ordinary matter would be profound, but extremely slow. Atoms are built from protons, neutrons and electrons. Take the protons away and the familiar chemistry that makes rocks, oceans, cells, and smartphones stops working. Over many eons, solids would lose atoms as protons inside their nuclei convert into lighter particles, like grains of sand slipping from a heap, only far slower than any erosion you see in daily life. A wooden table would not suddenly blink out, but the cumulative loss of nuclei would change the material's mass and structure. Planetary bodies would slowly lose mass and could eventually rearrange or dissipate as binding forces fail. The end state of such a process would be a universe increasingly dominated by low-energy particles and radiation rather than the complex, chemically active matter we live in. It's also useful to remember alternatives and limits. If protons are truly stable forever, then ordinary matter could persist until other processes, such as stars blowing apart or black holes evaporating, reshape the cosmos. Scientists keep testing, because finding proton decay would be a landmark clue about deeper laws of nature that unify forces and explain why the world has particle types it does. For everyday concerns, though, this remains a thought experiment with a dash of cosmic detective work, fascinating, slightly unsettling, and not something that will make your socks vanish tomorrow. Vacuum decay and quantum catastrophes. Empty space is not truly empty. It is threaded by invisible fields that set the rules for particles and forces. Sometimes those fields can sit in what physicists call a metastable state, a situation that looks stable but could, in principle, switch to a lower energy arrangement. Think of a marble resting in a shallow dent on a hillside. It seems comfortable until a small nudge or a rare quantum trick lets it drop into a deeper valley. That drop is the basic picture behind vacuum decay. Quantum mechanics allows rare events that classical intuition would call impossible, and one such event is tunneling, where a system moves through an energy barrier instead of going over it. In everyday life you can compare tunneling to a ball that somehow ends up on the other side of a hill without rolling over the top. It's not magic, just a very unlikely process. If a patch of space were to tunnel into a lower energy vacuum, a bubble of that new vacuum would appear and grow outward. Fast growth follows. The boundary of that bubble would race outward at essentially the speed of light, leaving the old laws of physics behind as it passes. Consequences would be extreme because the new vacuum could change particle masses and force strengths, in effect rewriting chemistry and nuclear structure. Atoms might no longer hold together. Cells, planets, and stars would not survive their structures. It is not like turning off a light, it is more like replacing the screws that hold matter together with glue that behaves differently. Short version, life as we know it would not persist inside the new vacuum. Scientists have thought carefully about whether anything we do could trigger such a transition. High-energy collisions created by particle accelerators were compared to natural collisions from cosmic rays and other energetic processes, and those comparisons make people less worried. In plain terms, the universe already runs more violent experiments than we do, and if those had triggered a catastrophe the cosmos would have shown signs. That practical check helps reassure researchers. Still, the phenomenon remains a topic of theoretical study because it ties directly into unresolved questions about why the universe has the laws it has. Detecting an oncoming vacuum decay would be essentially impossible. Because the bubble boundary would travel at light speed, no signal could outrun it to warn distant observers. You would either be inside the safe old vacuum or suddenly not. This is a grim but clear physical implication. For the curious mind, it motivates why scientists focus on understanding the energy landscape of fundamental fields rather than panic. Knowing the shape of that landscape tells us how likely such tunneling is. There are milder, everyday analogies that illuminate the danger without invoking doom. Supercooled water can remain liquid below freezing until a tiny disturbance makes it snap into ice all at once, releasing energy and changing structure. A small crack in the right spot on a dam can cascade into collapse. Cosmic humor helps here. You might call a vacuum decay a cosmic whoopee cushion, unexpected, fast, and guaranteed to change the atmosphere, except far less funny for anyone caught nearby. Overall, vacuum decay is a vivid theoretical possibility that teaches us about quantum mechanics, the fragility of apparent stability, and why physicists work so hard to chart the underlying landscape of nature. The destiny of photons, neutrinos, and background light. Photons are the little energy packets that make light, and they have several possible fates once they leave a star or a lamp. They can travel freely through space until something absorbs them, they can bounce off particles and change direction, or their wavelength can be stretched so much that they slide into lower energy forms of light. When a photon hits a leaf it can be captured and turned into chemical energy, which is how plants use sunlight, and when it meets a wall it often becomes heat, which is why a sunny spot on the floor feels warm. Some photons wander into the gravity wells of massive objects and get pulled in, never to come back, while others pass close to massive bodies and have their color shifted slightly by gravity, like a passing car sounding lower as it moves away, but for light. Neutrinos behave very differently, because they barely notice matter, they zip through planets, people, and buildings almost as if nothing is there. Produced in huge numbers inside stars and in other energetic processes, neutrinos mostly coast along without interacting, which makes them excellent messengers of places we cannot see directly. They also change identity as they go, switching between types in a way that could be likened to someone changing hats on a long walk. The hats don't affect their walking, but they do change how we can detect them. Detecting neutrinos requires giant, quiet detectors full of clear water or ice and a lot of patience, because catching one is like catching a whispered secret in a crowded room. Background light is the sum of all the faint glow that fills space from countless sources, and it evolves as photons travel. Some of that glow comes from dust-scattering starlight in our own solar neighborhood, producing the soft zodiacal light sometimes seen just before dawn, and other parts are the accumulated, stretched out light from distant sources that has shifted into infrared or even radio wavelengths as space expands. Local background light can warm dust, which then re-emits that energy at longer wavelengths. This is why cold dust shines in infrared rather than visible colors. Over time, many photons in this diffuse bath lose detectable energy and become part of a long wavelength whisper that is hard for our eyes to notice, though instruments tuned to those wavelengths can still pick up the signal. All three, photons, neutrinos, and the diffuse background, matter for how we understand and interact with the universe. Photons are everyday actors. They light rooms, charge solar panels, and warm your morning coffee spot. Neutrinos are the shy, ghost-like couriers that tell us about stellar hearts and cataclysmic events without getting tangled in the mess, and the background light is the accumulated memory of all past illumination, changing character as it drifts and cools. Detecting and interpreting them requires different tools and approaches, and sometimes a sense of humor helps. After all, photons are social and chatty, neutrinos are the introverts, and background light is the murmur of a very old, very large party. Remnants and possible survivors. When the last bright lights go out, what remains are a surprisingly familiar cast: burned-out star cores, compact dead stars, faint failed stars, wandering worlds, and the sparse fog of gas and dust between them. White dwarfs are the leftover cores of stars like our Sun. Think of them as hot embers that glow on their own for a very long time but no longer make new light the way living stars do. Neutron stars are even denser, compressed into a compact ball where matter behaves in strange ways that are hard to picture. A teaspoon of their material would weigh as much as a mountain on Earth. Black holes are regions where gravity is so strong that not even light escapes, and they can lurk quietly with only occasional fireworks when something falls in. Brown dwarfs sit awkwardly between planets and stars. They never got hot enough to truly ignite like a star, so they are dim, cool objects drifting through space. Rogue planets, untethered to any star, wander the dark alone, and the interstellar medium, thin clouds of gas and dust, still drifts through the emptiness like a faint mist. Among the actual physical remnants, planetary interiors can remain warm for a long time because of leftover heat and radioactive elements, so they are not uniformly frozen out. Deep beneath a planet's crust, heat can persist and create pockets where chemistry and even liquid water survive, fed by heat from the core or by chemical reactions in rocks. Hydrothermal vent communities on Earth show how life can thrive without sunlight by using chemicals instead. Bacteria there convert chemical energy into the building blocks of ecosystems, and whole communities of tube worms and clams depend on those bacteria. That's a good example of life hanging on where sunlight cannot reach, like a campsite powered by a slow-burning gas canister instead of a sunny day. Some organisms on Earth are built for extreme endurance and offer tangible models for biological survival in deep cosmic darkness. Tardigrades can curl into a dried-up ball and tolerate vacuum, very low temperatures, and high radiation for long periods by shutting down metabolism almost entirely, like a dozing cat that refuses to acknowledge the world. Certain bacteria, such as Deinococcus radiodurans, are famously radiation-resistant because they can repair their DNA after severe damage, which is handy if you're living next to a faint, crackling white dwarf or exposed to cosmic rays. Microbial life has been found kilometers below Earth's surface and in Arctic permafrost, demonstrating that life can wait out harsh surface conditions in protected niches. Spores and seeds show another strategy: dormancy. Some bacterial spores can simply pause their life processes until conditions improve, like a plant seed lying in soil until rain comes. Energy sources that could sustain life or machines when starlight is gone are varied and sometimes mundane. Radioactive decay inside rocks produces heat. Tidal forces from nearby massive objects can knead a world and create internal warming. Chemical gradients in rock and ice can provide the raw materials for metabolism. These are not fantasies, they're the same processes that drive ecosystems around deep-sea vents today. Machines, meanwhile, could endure by switching to ultra-low power modes, scavenging small energy inputs, or using local heat gradients. Think of a wind-up clock compared to a smartphone. If you conserve energy aggressively and can tap a tiny, steady source, you stretch survival dramatically. Backup systems, durable materials, and redundancy all help, and human-made artifacts buried in protective vaults or in shadowed craters might persist far longer than expected. Yet survival is not guaranteed. The long-term prospects depend on both the local environment and the strategies organisms or machines use. Surface dwellers that rely on sunlight are effectively stranded, while those that can exploit internal heat, chemical energy, or robust dormancy stand a chance. Technological survivors would need to cope with gradual decay of parts and the slow loss of accessible energy, but design systems that can enter deep hibernation, repair themselves, or repurpose local materials could persist. In short, the remnants are physical and often familiar, and the possible survivors are those that adapt to scarcity, tucked-away microbes, hardy cryptobians like tardigrades, and, conceivably, engineered machines that learn to live on crumbs of energy. A tiny ecosystem around a warm rock fracture could be as lively, in its own way, as a backyard pond, just much colder and a lot less photogenic. Immense time scales, from billions to googolls. Numbers like a billion and a googol sit on the same number line, but they live in entirely different neighborhoods. A billion is exactly 1 followed by 9 zeros, written as 1, 0, 0, 0, and a googol is 1 followed by 100 zeros, written as 10^100. To make those dry symbols feel real, a billion seconds is roughly 3 decades. Short enough to remember a childhood home, long enough to learn a language well. Counting at 1 number per second gives useful intuition. It takes about 31.7 years to reach a billion. Slow, steady tasks add up over decades. A billion minutes, however, stretches to roughly 1900 years, which is a span that comfortably contains whole civilizations. 1 billion hours equals more than 100,000 years, which is a time frame that can erode mountains. These conversions help because words like billion can be slippery. Turning them into seconds, minutes, or hours makes the idea concrete without complicated jargon. A googol does not sit politely on that same scale. It's 10^100, a digit 1 followed by 100 zeros, and it is used mainly to show how utterly huge a number can be. There are far fewer atoms in a typical estimate of the observable universe. Figures like 10^80 are often quoted, than there are in a googol, so a googol is more of a mathematical giant than a physically meaningful count. If you tried to write out a googol in full decimal form, your sheet of paper would be useless. You would run out of ink, patience, and probably paper mills. Practical life rarely requires googol-sized thinking. Economies, populations, and even planets operate in numbers where billions are meaningful and measurable. Scientists and engineers use billions to discuss distances, ages, or quantities they can observe and test. Googols mostly live in thought experiments, jokes, and the story of a popular company name that plays on the idea of an enormous number. In computing, algorithm designers worry about exponential growth because it quickly becomes impractical. A function that doubles every step will hit billions fast, and after a few more doublings it will seem to explode into numbers that are simply unusable. Everyday examples help keep perspective. Saving $1 a day gets you to $1 million in far less time than reaching $1 billion, and humans rarely need more than billions of seconds to plan a career or a lifetime. Humor helps too. If waiting in line for 5 minutes feels eternal, discussions of billions and googols will remind you that human impatience is comically small on the cosmic scale. Still, these large numbers are useful tools. A billion gives concrete scale to things we can measure, while a googol is a reminder that some notions of huge are only meaningful in the realm of ideas. How scientists model the far future. Scientists build far future models on bedrock principles we trust because they work in many places: gravity pulls, nuclear reactions power stars, and energy spreads out instead of piling up. They take measurements from lab experiments and telescopes, then use those reliable pieces like building blocks. Think of it as using a proven recipe. If you know how sugar caramelizes and how heat moves through a pan, you can make a dessert. If you know how atoms interact and how gravity behaves, you can sketch how a star will behave. This gives models a strong starting point, even when the eventual pictures look strange compared with everyday life. Computers are the workhorses that let scientists push laws forward in time, step by step. A model breaks a big, messy problem into many small updates, like following a recipe one instruction at a time. Sometimes the steps are very small and there are many of them, sometimes a larger, simpler step is enough. To test how reliable a prediction is, researchers run ensembles, lots of similar simulations with slightly different inputs, which is like baking the same cake with slightly different oven settings to see how sensitive the result is. A little randomness is often added on purpose, too, and that helps capture the role of chance. Imagine shaking a jar full of marbles repeatedly to see the range of ways they can settle. Uncertainty grows with time, so scientists don't give single, rigid stories for the deep future, they build families of possible outcomes instead. Some results are robust and don't depend on tiny details. For example, if a process is driven by a law that always points the same way, many different models agree on that general trend. Other outcomes depend strongly on unknowns, like whether certain particles decay or whether new physics exists. Those questions can open up entirely different branches of possibility. Scientists therefore separate what they know from what they don't, and they label predictions by how confident they are, much like traffic reports that say, heavy but moving, versus, stopped. Models are constantly checked against what we can observe now and nearby in time. Astronomers look at many stars at different life stages and compare those snapshots to model predictions, much as a doctor checks growth charts for children rather than waiting for the final height. Laboratory results and precise measurements from space missions constrain the options, pruning out wildly speculative branches. And when gaps in knowledge remain, researchers explore alternatives explicitly, describing how different assumptions change the outcome. That honesty about limits, combined with clever use of computers and simple analogies, turns the daunting task of modeling the far future into a disciplined, if humble, scientific enterprise, and occasionally into a thought experiment that makes for good conversation at parties. Observational clues and empirical limits. Astronomers can already see that galaxies are making fewer new stars now than they did earlier, and that decline is one of the main clues suggesting a long, slow fade toward a darker cosmos. Surveys that look at ultraviolet light and infrared glow from distant galaxies act like census takers. Bright young stars give off lots of UV, while dust heated by star formation shines in the infrared. By comparing the light from many galaxies at different distances, scientists piece together how fast stars were born at various stages, and the trend points downward. Think of it like checking traffic cameras on a highway and noticing the rush hour has thinned. The pattern tells you something about how busy the road will be later. Faint, cooling stellar remnants also leave traces that hint at the future. White dwarfs, the leftover cores of medium-sized stars, slowly dim over time, and the distribution of their brightness in nearby star clusters helps calibrate how stars fade when fuel runs out. Observers can measure that faint glow directly in our own galaxy. It's like watching embers in a fireplace to learn how quickly a fire dies. On the other hand, tiny, cool red dwarf stars burn their fuel very slowly and will keep shining long after brighter stars have gone. Their sheer numbers and long lives mean they are important when predicting a dim, late-time universe, but we still rely on models to estimate how their collective light will change far into the future. Background light and relic radiation offer further clues, but also expose practical limits. The cosmic microwave background, a faint afterglow from the early universe, is one kind of fossil radiation that telescopes can measure today. However, as light stretches with cosmic expansion it becomes harder to detect, and other low-energy backgrounds, like the diffuse glow from all-past starlight, called the extragalactic background light, are extremely faint and easily lost in local foregrounds such as interplanetary dust. Ground and space-based instruments suffer from noise that limits sensitivity. Thermal glow from the telescope, zodiacal light in the inner solar system, and the Milky Way's own scattered light all act like a fog that hides subtle signals. It's the observational equivalent of trying to spot fireflies through a car windshield smeared with fingerprints. There are fundamental empirical limits as well, beyond just instrument sensitivity. Light travels at a finite speed, so telescopes show us the past, not the future, and cosmic expansion can push regions of space beyond a horizon where their light will never reach us again. That means some of the most interesting late-time behaviors are inherently unobservable. We can model them but we cannot measure them directly, like predicting how a sealed jar will smell in 1,000 years without actually opening it later. In addition, many predictions depend on ingredients we have not fully measured. Properties of invisible components such as dark energy and dark matter influence how structures merge and fade, and uncertainties there create a fog of their own in long-term forecasts. Practical examples help. If your camera's battery dies while taking a time-lapse, you can make reasonable guesses about the last frame, but you can't claim you actually saw it. Observational strategies try to work around those limits by using multiple, cross-checking clues. Stellar population studies, deep sky surveys, measurements of faint background light, and searches for low-energy particles like neutrinos each offer different pieces of the puzzle. Putting them together reduces reliance on any single uncertain assumption. Still, some questions remain inherently outside empirical reach. No matter how many telescopes we build, we cannot watch the true final epoch directly, and some signatures will be so weak that foregrounds and cosmic variance drown them out. That doesn't mean the subject is hopeless, it just means predictions combine solid, measurable trends with cautious extrapolation, and occasionally a bit of optimistic detective work, which is science's way of being hopeful without being reckless. Unknown physics that could alter the fate. Measurements of distant supernovae and maps of the sky show that space is stretching faster now than simple gravity alone would predict, and observations of galaxies reveal more pull than visible matter can explain. Scientists name these puzzles dark energy and dark matter, but those are labels for ignorance, not answers. Evidence comes from concrete effects. Stars in the outskirts of galaxies orbit too quickly for the gravity of the visible stars to hold them, and light from faint, invisible clumps bends background starlight in ways that reveal hidden mass. Simple everyday images help here. Picture a balloon dotted with raisins for galaxies and invisible glue between them that nobody can see, yet it changes how the raisins move. If the rules of physics we take for granted are incomplete, then the large-scale destiny of everything could be different from our usual scenarios. One plain possibility is that the driver of acceleration could slow or stop, letting gravity eventually win and halt expansion. Another is that it could strengthen and tear structures apart. Think of the universe like a loaf of bread rising in an oven. Change the yeast mid-bake and the texture comes out entirely different. People often call these outcomes heat death, big rip, or big freeze in scientific discussions, but the key idea is that small changes in the underlying laws produce very different long-term behavior. It is a bit like adjusting the thermostat on a very slow oven. The effect is subtle at first and catastrophic later. Unknown properties of dark matter are an especially practical avenue for altering fate. Current facts show dark matter acts mostly like invisible, collision-less stuff that clumps and holds galaxies together, inferred from motions and gravitational lensing. If instead this dark component interacts more with itself or with ordinary matter, then galactic structures could evaporate, merge, or behave in unexpected ways. A kitchen analogy applies. If the flour you use for dough suddenly started sticking differently, your bread would not rise the same way. The recipe of the cosmos depends on how these invisible ingredients behave. Experimental efforts underground, in space, and at particle accelerators aim to test these interactions, and those experiments are based on observations we already trust. Quantum-level oddities could also have outsized consequences despite their tiny scale. Quantum fluctuations are real and left fingerprints that grew into galaxies. That is a fact observed in the cosmic background radiation patterns. Theoretical ideas suggest that a tiny, unstable region in empty space could trigger a larger change, like a microscopic crack that propagates through a crystal. Everyday experience with supercooled water or a jar lid suddenly popping open gives a useful picture. A calm-looking system can flip to a new state without warning. While such transitions remain speculative, they are grounded in the same quantum principles that power modern electronics and chemistry. Finally, practical stakes make these possibilities more than academic curiosity. Telescopes mapping the distribution of galaxies, detectors trying to catch dark matter particles, and precision tests of gravity on Earth are all ongoing, because the answers affect predictions about the universe's long-term behavior. If new laws are found, technologies might shift and scientific planning for far future exploration would change too. It is not just abstract doom or salvation. Understanding these unknowns could influence how we interpret everything from the stability of atoms to the evolution of galaxies, and it gives scientists a grand excuse to keep building clever experiments, which is a win for both knowledge and lab funding. Cosmic recycling, bounces and creations. Some scientists explore the idea that the universe might not be a one-shot show but instead goes through cycles where contraction is followed by a rebound, like a great cosmic bounce. In everyday terms, that bounce is like compressing a spring and letting it fly back. The universe tightens and then expands again, not unlike a breathing organism on a colossal scale. These models are attempts to explain how space, time, matter, and energy could be reshaped over and over, rather than simply appearing once and fading away. Think of it as a very slow-motion version of a ball dropped on the pavement that doesn't just stay flat but somehow finds a way to spring back up. Stars act as the hard-working recyclers in this picture, taking simple gas and building more complex stuff through a process called fusion, which is just atoms sticking together and releasing energy. When a massive star reaches the end of its life, it can explode and fling those heavier elements across space, seeding clouds of gas with the raw materials for new stars, planets, and ultimately life. A helpful life example is the kitchen. Combine flour, eggs, and butter and you get cake, and when the cake crumbs are scattered they can feed new beginnings, although with less glamour than a supernova. Our own bodies contain elements forged in ancient stellar furnaces, so in a literal sense people are part of that cosmic recycling chain. Not all recycling is perfect, however, and that same issue shows up on cosmic scales. Entropy, which you can think of as the tendency for things to spread out and get messy, makes full recovery challenging after each cycle. This is similar to throwing out a plastic bottle and finding it has been downcycled into lesser material. The original form is gone even if some atoms remain useful. Some proposals try to explain ways the universe could reset or sidestep that messiness, but those ideas are still being tested and debated. In the meantime, the practical takeaway is simple: the cosmos rearranges its parts, and each rearrangement builds new opportunities out of old leftovers. Astronomers look for hints that past cycles might have left fingerprints, subtle patterns in the background glow of the universe or unusual distributions of galaxies could be clues, and they use telescopes and simulations to search for them. Black holes and collisions between galaxies also play a role in the ongoing turnover, concentrating and then redistributing matter in ways that feed future structure formation. And while the picture is grand and sometimes mind-bending, it has a comforting everyday echo. Just as compost turns kitchen scraps into garden soil, cosmic recycling turns the remains of old stars into the ingredients for new worlds, which is both scientifically fascinating and mildly reassuring for anyone who overcooks dinner. Multiverse ideas and their implications. Physicists have sketched several ways the universe might not be the only one, and each sketch comes with plain language ideas you can picture at home. One idea comes from quantum mechanics. When tiny events happen, like an electron choosing a path, some interpretations say the universe branches so every outcome happens in a separate branch. Another comes from the idea that space can stretch unevenly. If different regions stop stretching in different ways, they could become separate, bubble universes with their own rules. A third comes from theories that add extra dimensions or layers to reality. Think of our universe as a sheet of paper floating beside other sheets, each sheet its own world. There is also the suggestion that all mathematically consistent realities exist as real places, an abstract but simple proposal that turns math into a kind of cosmic real estate. These are not just fanciful words, they are different attempts to explain observations and to reconcile the math that describes nature. Testing these ideas is hard, which matters a lot for scientists. Some proposals could leave faint traces we might detect, such as slight patterns in the leftover glow from the early cosmos if two expanding bubbles bumped into each other. Many proposals, however, predict realms forever out of reach, so they push the limits of how science usually works. That leads to a practical consequence: researchers must design clever tests and refine predictions, otherwise the ideas remain philosophical. In everyday terms, it is like hearing a rumor about a neighbor and deciding to check the backyard camera rather than accuse them at dinner. Evidence still rules. This difficulty also shapes funding and research priorities, because experimental work is expensive and scientists like to put resources where a clear test exists. Beyond physics, these ideas ripple into philosophy, ethics, and how people make decisions. If every quantum choice spawns a new branch, questions about personal identity arise. Which version of you counts as you? Practical life stays the same, though. Choosing whether to take a new job still changes your life here, even if a version of you stayed home elsewhere. The notion that many environments exist can also soften the fine-tuning problem, the observation that physical laws seem set up to allow life, by suggesting we live in a place compatible with life simply because places that aren't compatible don't host observers. This is often called an observer selection effect and is less mystical than it sounds. It's like only finding umbrellas in a store because people in that town buy them when it rains. There are real-world, everyday uses for thinking in multiverse-like ways, too. Business planners run scenario analyses that are essentially creating alternate futures to prepare for risk. That same habit of mapping possibilities helps engineers design safer systems and helps policymakers plan for rare disasters. In tech, some popular explanations of quantum computing mention branching outcomes, though one must be careful. The practical workings do not require belief in any one philosophical picture. And for storytellers and artists, these ideas provide fertile soil for new plots and striking visuals. A little humor helps here. Treating the multiverse as an excuse for bad behavior won't fly. The taxman doesn't accept first was acting in another branch as a deduction. The core takeaway is pragmatic. These ideas stretch how we think, motivate new experiments, and change how we frame questions about probability, causation, and meaning, even if definitive evidence remains elusive. Entropy, information, and the arrow of time. In everyday terms, entropy is a way to count how mixed up or spread out energy and stuff have become, while information measures how much specific detail you have about where that stuff is. A tidy desk where every pen and paper has a place has low entropy and lots of usable information about where things are. A desk after a busy week has high entropy and you would need to spend time and effort, mixing energy into the system, to recover the original order. Short sentence. Information in this sense is simply a measure of surprise. The less surprising an outcome, the less information it carries. For example, getting the same predictable weather report every day carries little new information, but an unexpected thunderstorm suddenly tells you a lot. A shuffled deck of cards holds more information to describe every single card's position than a stack sorted by suit, because the shuffled order is more surprising and requires more detail to specify. This idea connects to how we compress files on a computer. Repeated patterns can be described with fewer bits, while random-looking data resists compression. Entropy and information are two sides of the same coin when you look closely. If you know every microscopic detail of a system, where every molecule is and how fast it's moving, you have a lot of information and the entropy is low. If you only know coarse facts like the overall temperature, you have lost microscopic information and the entropy is higher. A practical example is stirring milk into coffee. After stirring, the milk and coffee are evenly mixed and you no longer have information about which milk molecules started where. You can't unmix them just by waiting, because doing that would require recovering lost microscopic details. Brief pause. Thought experiments help make this concrete without heavy math. One famous idea imagines a tiny being that could measure and sort fast and slow molecules to make heat flow backward. At first it seems to break the rule that entropy grows. But measuring and using that information costs energy and produces heat elsewhere, so the total amount of disorder still goes up. That shows how information processing is physical. Erasing or resetting a memory requires energy and creates heat, which is why computers generate warmth while they work. Another plain-life example, clearing your email inbox feels like creating order, yet the electricity and cooling needed to run the servers and your device generate waste heat and raise entropy overall. The arrow of time, the reason we remember the past but not the future, comes from the statistical tendency of systems to move from less probable, low-entropy states to more probable, high-entropy ones. Heat naturally flows from hot to cold, glasses fall and break, and cream mixes into coffee. The reverse processes are astronomically unlikely without deliberate intervention. Short sentence. Still, local pockets of decreased entropy are possible. Living cells build complex molecules and refrigerators make cold inside, but they do so by exporting disorder to their surroundings, so the universe's total entropy increases. Practical consequences touch computing, engineering, and daily life. Data centers must shed heat as they process more information. Efficient algorithms save energy and, indirectly, slow the increase of waste heat. When you back up and then delete large files, the physical devices handling those operations shift energy around and produce heat even if the files are just zeros and ones. A little humor helps here. Your laptop getting warm during a video call is just entropy making itself comfortable. Altogether, thinking about entropy, information, and the arrow of time ties abstract ideas to things you see every day: messy rooms, cooling coffee, and busy processors, showing that the flow from order to disorder is not mystical but rooted in how information, energy, and probability play together. Can life, or intelligence, persist? Stars will eventually stop shining brightly in most places, leaving the cosmos cold and thin, and that matters because life depends on usable energy differences to do anything at all. Energy comes in many forms: light from stars, heat from a planet's interior, chemical gradients in rocks and fluids. Organisms on Earth make a living by tapping those differences. For example, microbes at ocean vents eat chemicals spewed from the seafloor, and plants collect sunlight. When those sources dwindle, everything that relies on them faces a practical problem: no energy, no work, no maintenance of complexity. Life already shows surprising tricks for surviving decline. Many microbes can drop their metabolism to a sliver of activity and essentially wait. Spores and seeds can sit dry and dormant for very long periods, and tiny animals like tardigrades can dry out and later rehydrate to life. Deep underground, bacteria eke out a living by slowly processing rock and water, at rates that put human patience to shame. These are real examples of life persisting by slowing down rather than trying to keep sprinting on an empty fuel tank. It's like a very extreme version of sleep until breakfast, except breakfast is a chemical reaction in a dark rock. Intelligence, being a form of organized, energy-hungry activity, faces similar choices but with more options. One route is migration, moving to stars that burn more gently and steadily, such as small, cool stars that give off usable light for a long time. Another is engineering, building large collectors to capture and concentrate whatever energy is available. The idea behind a Dyson-like structure is to surround a star with devices that convert as much starlight as possible into useful work. A third path is changing form. Brains made of wet biology are costly to maintain. Switching to machine substrates or low-energy computation could let minds keep running on far less power. We already see the first steps toward this with ultra-low-power electronics and research into long-term data preservation. Think of it as trading a gas-guzzling car for a tiny solar scooter when the highways get empty. In the very deep future, the game changes because the universe tends toward uniformity, heat spreads out and useful energy differences become scarcer. That tendency is what physicists call entropy increasing, which just means things get more even and less able to do work. There are speculative ways to cope: cycles of deep hibernation, performing mental tasks extremely slowly to stretch limited energy, or even harvesting tiny trickles of energy from exotic sources like the faint emissions that black holes are thought to give off. Those emissions are theoretical but arise from solid physics. In plain terms, a black hole isn't an eternal sink. Under the right view it releases a whisper of energy that, with clever engineering, could be put to use. Still, there are real limits imposed by basic physics, so eternity becomes a matter of how cleverly life and intelligence can stretch resources, rather than a guaranteed forever. Practical, present-day actions point toward resilient strategies that would help persistence a lot. Redundancy matters. Keeping copies of essential information in many locations and formats reduces the chance everything is lost. Hard, inert storage like etched rock, silica glass, or other radiation-tolerant media can outlast ordinary electronics. Dispersal helps, too. sending archives to asteroids or the outer parts of systems reduces the risk of local catastrophes wiping out all records. Biological strategies also apply. Cultivating microbes that recycle waste and reclaim scarce nutrients is a low-energy way to maintain a small, self-sustaining ecosystem. These are things people can work on now without inventing warp drives. So can life or intelligence persist? Yes, but with reservations. Persistence looks more like adaptation and stretching than immortality, migrating to better niches, changing computational habits, going dormant when needed, and designing robust systems to survive isolation and scarcity. Life on Earth provides concrete examples of resilience, and engineers already pursue low-energy computation and durable storage. A little creativity, a lot of redundancy, and the willingness to nap for geological stretches could keep a spark of intelligence going long after easy energy is gone, though asking for everlasting consciousness is probably asking for too many cups of coffee from a slowly cooling universe. Technologies to delay or escape darkness. Cities and households already use a mix of simple and advanced tools to keep darkness at bay, and many of those same ideas scale up if the lights truly go out on a cosmic scale. At the home level, swapping old bulbs for LEDs cuts the power needed for light by a big margin. Batteries and uninterruptible power supplies keep a router or fridge running for a while. Portable generators kick in when the grid fails. Think of a phone power bank and a camping solar charger, but multiplied to keep a neighborhood humming. Those are practical, everyday technologies that buy time. For neighborhoods and towns, the answers get more structural. Microgrids let a small area run independently from the main grid, using local solar panels, wind turbines, and battery banks. Batteries at utility scale store extra energy when the sun is out and give it back at night. Pumped hydro plants use water pushed uphill like a mechanical battery, while geothermal taps heat from below the ground for steady power. Nuclear reactors provide continuous electricity without depending on the sun, and geothermal or biomass plants can do the same in certain places. A useful example is a campus that can run on its own microgrid during city outages. It's like a self-sufficient electric neighborhood. Keeping people alive when sunlight or external supplies are gone requires closed environmental systems. Spaceship-style life support recycles air and water, filters remove carbon dioxide and bacteria, and water purification systems recover most used water for reuse. Hydroponics and vertical farming let food grow indoors with artificial light and nutrient-rich water instead of soil. These systems are like a tightly run home aquarium or a backyard compost loop, but engineered so that oxygen, water, and food circulate with little waste. Simple tests at home, composting kitchen scraps and saving gray water for plants, are small versions of the same principles. If the goal is not just to delay darkness but to move away from it, propulsion technologies matter. Chemical rockets remain the workhorse for lifting mass from a planet, while ion drives push spacecraft gently but very efficiently by accelerating charged particles. They're slow to start but excellent for long trips. Solar sails catch light like wind in a sail, using steady pressure from photons to accelerate without carrying propellant. Researchers are also exploring ways to use nuclear heat either to boil propellant faster or to generate electricity for electric engines. Both approaches promise stronger, more sustained thrust. There's also experimental thinking about using powerful ground lasers to push tiny, lightweight probes into interstellar space. Each method has trade-offs: speed, fuel needs, and engineering challenges. It's like choosing between a sports car, a long-distance cruiser, and a bicycle with a big tailwind. Shielding and resources determine survival on the move. Water and soil can serve as cheap, effective radiation shields, and building habitats from local rock or dust means you don't have to haul everything from home. Mining asteroids or moon regolith to extract metals and oxygen is the space version of using local lumber to build a cabin. Manufacturing in space, 3D printers that use local feedstock, reduces dependence on long supply chains. These approaches turn raw space dirt into usable shelter and propellant, making long journeys or independent habitats more realistic. Practical steps that matter now include improving grid resilience, expanding battery storage, and investing in efficient lighting and local renewable power. Supporting research into higher efficiency reactors, long-duration batteries, and advanced propulsion broadens future options. And a little humor helps, keeping a robust backup plan for your house, a good lamp and some spare batteries, is the civilian version of the technologies engineers design for whole cities or spacecraft. Small actions and big inventions together offer the best chance to delay darkness, or, if needed, to head for brighter places. Ethical and philosophical perspectives. As stars run through their nuclear fuel, they change, dim, and eventually stop producing the light and heat that sustain familiar processes. Many cosmologists discuss scenarios where, over extreme timescales, the universe becomes ever colder and darker, a backdrop that raises unusual ethical questions. This diminishing of stellar light is more than an astronomy problem. It forces a reckoning about what matters when the conventional stages of life and civilization can no longer continue. People tend to think in human lifespans, but ethical thinking must stretch if the stakes include far future beings, or even the possibility that no conscious life remains at all. The first practical ethical issue is responsibility across time. Do we owe duties to people and beings who will exist far beyond our lifetimes? Think of leaving a garden in better shape for grandchildren, or creating a detailed will so your heirs won't fight over the toaster. Those are immediate, relatable examples. On a cosmic scale, the same logic asks whether we should preserve knowledge, reduce existential risks, or conserve resources for distant descendants. Practical actions today, like supporting long-term archives or maintaining biodiversity, mirror those deeper duties and are easier to imagine when grounded in everyday analogies. Different philosophies answer these duties in varied ways, and simple labels help clarify the choices. One view places humans at the center. Value comes mainly from human lives and projects. We should then focus on things that directly improve human well-being now and in the near future. Another view widens the circle to include all possible future sentient beings, giving moral weight to ensuring conditions that could support life far down the road. A third stance treats the cosmos itself as having value independent of observers, seeing the persistence of order or beauty as intrinsically worth protecting. These positions lead to different policies. Short-term helpers prefer hospitals and schools. Long-term thinkers fund archives and planetary protections. Practical trade-offs quickly appear when you try to act on these philosophies. Conserving resources for a distant future can mean fewer resources today for the poor, the sick, and the vulnerable. It's like choosing between fixing your roof now or investing in an insurance policy that might pay out decades from now. Small, tangible steps show how people balance these concerns. Global seed vaults and cultural archives aim to safeguard options for the future without requiring everyone to freeze their lives, and outreach projects hew to present needs while also building durable institutions. There's also a moral question about messaging. Sending probes with messages for unknown future finders is a hopeful act, similar to leaving letters for unborn grandchildren. It feels noble, and a little romantic, but it does not substitute for feeding the hungry today. Philosophically, the darkness after the stars prompts reflection on meaning and value. Does meaning depend on an enduring cosmos, or can it be created moment by moment? Many thinkers argue that meaning is constructed through relationships, projects, and shared commitments. That implies meaningful lives can exist even if the universe trends toward greater solitude. Artists compose for future listeners. Scientists lay groundwork knowing their work may be read only by successors or none at all. Humor helps here. Write a song even if only the moths will be the audience, yet the deeper point remains: a universe without eternal light can still host meaningful human action. Finally, ethical thinking about such distant futures should inform present policy without becoming paralysis. It is sensible to support robust, realistic measures, science that reduces clear risks, institutions that preserve knowledge, and social programs that maintain civic resilience, while avoiding extravagant sacrifices that harm people who live now. Balancing immediate compassion with prudent stewardship looks a lot like good household management: pay the bills, keep the lights on, and tuck a little into savings. The long view invites humility, careful planning, and a dash of optimism, because our choices ripple farther than we often admit, and a well-timed act of kindness can be a tiny lamp in a very long night. Cultural responses, stories, art, and meaning. Across cultures, creators have repeatedly turned the idea of a final, starless sky into powerful symbols in stories, visual art, music, and ritual. Writers often set small human dramas against vast, empty backdrops to test characters' hearts and choices. For example, Cormac McCarthy's sparse novels strip away comforts to focus on moral decisions in a ruined world. Filmmakers do something similar. A silent, empty landscape on screen forces viewers to listen harder to small human sounds, breathing, footsteps, a child's laugh. Musicians working in ambient or minimalist styles build slow, spreading textures that feel like walking into a dark room where your own thoughts echo back. Brian Eno's soundscapes are a clear real-world example of composers crafting atmosphere rather than songs, turning silence and sparse tones into a kind of storytelling. Storytelling traditions use the idea of cosmic endings to teach and comfort in simple ways. Folktales often turn big, scary things into personified figures you can bargain with or outwit, which makes them less terrifying at bedtime. In modern fiction, authors use cosmic bleakness as a mirror for present-day anxieties. Stories about a final night can actually be about loneliness, loss of community, or social breakdown. Some community rituals borrow the imagery too. Gatherings at dusk, candlelit vigils, and communal meals use low light as a shared experience that binds people together, turning the dark into a space for memory and connection rather than only fear. Even power outages produce impromptu storytelling sessions in neighborhoods, with families telling jokes and swapping recipes by flashlight. Darkness becomes a prompt for closeness. Visual artists treat absence of starlight as an artistic tool, often using black, deep blues, and void-like spaces to invite viewers into reflection. Painters like Anno Domini Reinhardt explored near-black canvases that force the eye to find subtle shifts. Viewers spend time with the work because there's nothing obvious to chew on. Installation artists play with light and dark too. Darkened rooms or single-beam illuminations create a sensation of being inside a thought, not just looking at an image. Public art projects that deliberately dim lights or create dark rooms in urban festivals show how absence can be curated to produce awe and collective calm, a sort of cultural nightlight. Photographers, meanwhile, document empty skies and abandoned observatories to show how silence in the heavens can mirror human silence on Earth. Meaning-making around a starless idea often mixes melancholy with practical lessons, and sometimes a dash of gallows humor. Some activists and writers use cosmic end scenarios to highlight present risks, pointing out that treating today's environment poorly is a short-sighted way to plan for any future, celestial or otherwise, so the metaphors encourage stewardship rather than doom. Therapists and art therapists harness the theme too. Clients draw or sculpt voids to externalize grief, then fill them with color or objects as a form of repair. Everyday examples are simple and human. Neighbors organizing blackout potlucks, poets composing ekphrastic poems about empty skies, comedians cracking jokes to ease collective worry. If the stars go out, at least we can save on glitter, someone might quip, small levity that helps. Across all these responses, the common thread is transformation. What could be sheer terror becomes a canvas for meaning, a place to rehearse hope or build solidarity. People turn cosmic emptiness into parables, installations, songs, and rituals that teach, heal, criticize, or console. The result is cultural work that doesn't need to predict the end of everything to be useful. It simply gives communities tools to talk about loss, to laugh a little at the dark, and to choose actions that matter in the here and now. Why studying the far future matters now? Choices made today shape systems that will last for many future generations, so studying the far future is not idle daydreaming but a practical tool for better decisions. Long-lived things, like cities, legal systems, power plants, and seed banks, can lock in benefits or harms long after the people who built them are gone. For example, a poorly sited dam or a short-lived digital archive can create problems that are expensive or impossible to fix later. Thinking ahead helps engineers, planners, and communities avoid those traps. Preserving knowledge and materials is a concrete reason to look ahead. Physical media degrade and file formats change, old photos on floppy disks and home videos on VHS often end up unreadable because the devices to play them disappear. Vaults for seeds and institutions that store cultural records are real-world responses to that problem. When scientists and librarians consider the far future, they choose durable materials, open file formats, and redundancy, basically, not putting all your family photos on a single, ancient thumb drive. That kind of planning is as practical as labeling boxes in the attic so that your great-grandchildren don't have to hire a digital archaeologist. Reducing large-scale risks is another urgent motive. Some dangers could cause widespread, long-term damage if not addressed early. Common-sense measures taken now, research, monitoring, safety rules, and international agreements, can greatly lower those risks. Think of it like having smoke detectors and a fire escape plan for civilization. Modest effort up front saves a lot of trouble later. Practical steps include better disease surveillance, careful handling of powerful technologies, and protection of essential infrastructure. These efforts are about creating buffers and backups, not about predicting every possible future. Studying the far future also reshapes incentives and values in useful ways. When policymakers and businesses factor in impacts on people not yet born, they make different choices: more maintenance of roads and bridges, more attention to biodiversity, and more cautious bets on risky shortcuts. A neighborhood that plans green spaces and proper drainage now will save money and grief later. It's like choosing a sturdy pair of shoes for a long hike rather than cheap flip-flops that fall apart after 1 mile. Your feet, and future residents, will thank you. Small, realistic changes in today's laws, investments, and habits add up to big benefits down the line. Finally, planning for the far future encourages humility and flexibility. Knowing that we cannot foresee every twist, we build systems that can adapt: modular infrastructure, open scientific practices, and policies that can be revised when new information appears. That mindset reduces costly overcommitments and leaves room for better solutions as knowledge improves. And if nothing else, thinking this way gives people permission to be a little more thoughtful, less like someone leaving a messy kitchen behind, and more like a neighbor who labels where the cookies are. Key questions driving future research. The far future of the cosmos raises clear, practical questions that scientists are racing to answer, because every one of them changes what darkness after the stars would actually look like. One major question asks whether the push that makes space grow faster, what scientists call dark energy, is a constant push or something that changes over time, and that matters because a steady push slowly leaves galaxies isolated while a changing push could lead to very different outcomes. Researchers study the pattern of galaxies and how light from faraway explosions dims to probe this, much like watching the traffic on different roads to guess whether a city will sprawl or freeze in place. The comparison is simple: if the expansion keeps accelerating, distant objects will slip beyond sight and communication, like watching the tail lights of cars vanish on a never-ending highway. Another foundational question concerns the stability of ordinary matter, starting with protons, the particles that make up atomic nuclei. If protons are absolutely stable, atoms can persist for unimaginably long times. If they can decay, then everyday matter will slowly dissolve into lighter particles and radiation. Underground experiments with huge tanks of pure water and sensitive light detectors are listening for the faintest signs of such decay, similar to how someone might sit in a quiet room waiting for the tiniest creak in an old house. So far no decay has been seen, which keeps the hope alive that some form of matter stays around, but the search continues. Black holes pose another set of pressing questions because they store huge amounts of mass in a very small space and warp the rules of physics. Theoretical work suggests black holes can slowly lose mass by emitting a trickle of particles, a process often called Hawking radiation, yet no direct observation of this radiation exists because it would be vanishingly faint for large black holes. Physicists also ask whether information swallowed by a black hole is truly lost or somehow preserved, a puzzle that plays out like whether shredding a document erases its content forever, or whether tiny bits of the pattern survive in the ashes. Progress comes from studying black hole surroundings, gravitational waves from their collisions, and clever theoretical models that try to reconcile the clash between gravity and quantum rules. Questions about whether new kinds of matter or physics could appear far in the future are also central to planning research. Could exotic particles, unknown forces, or subtle quantum effects rescue complexity or enable strange phases of the cosmos? Laboratory analogues, systems in which fluids, cold atoms, or electrical circuits mimic cosmic behavior, help test ideas that are otherwise impossible to probe directly, much like using a model train set to understand how a real railway junction behaves. These tabletop experiments are surprisingly useful and often point the way toward the measurements astronomers should try to make with telescopes and detectors. Practical detection strategies form another important line of inquiry. What signatures would tell us that one of these dramatic late-time processes is happening? Scientists look for very faint, low-energy photons, unexpected particle fluxes, tiny changes in the overall expansion rate of space, and subtle ripples in spacetime. Building ever larger and quieter detectors, improving calibration and long-term monitoring, and combining different types of observations are the tools of the trade, like upgrading from a flashlight to a lighthouse when you want to spot a far-off ship. The emphasis is on cross-checks. A suspicious signal in one channel should match patterns in others before anyone writes headlines. Finally, researchers are driven by the question of whether any form of organization, such as structures that could sustain complexity, can survive in the long run and under what conditions. This ties back to all the other questions, because the answers determine whether energy sources remain, whether matter persists, and whether isolated pockets of the universe might still host processes of interest. That curiosity mixes serious science with a pinch of human stubbornness. After all, thinking about survival strategies for the cosmos is a bit like planning for a very long camping trip. Pack enough batteries, keep the campfire rules simple, and maybe bring a friend. So, we end up in a universe where the big, bright parties are over, stars burn out, the sky grows darker, and heat thins until only faint traces of light or slow, sleepy particles remain. Think of it like a campfire that finally turns to cold embers, beautiful memories, but not much warmth left. Even the densest leftovers slowly fade away, not because of drama, but because the universe keeps stretching and cooling. Quick recap of the main points. Stars are temporary, they shine, age, and stop shining. Space keeps stretching and cooling, so light gets weaker over time. Big, heavy objects like black holes fade very slowly, leaving an almost silent, dark cosmos. You might wonder what that means for us. For now, it's far, far in the future, not something your morning coffee needs to worry about. But thinking about it helps us appreciate how alive and special the present is. It's like knowing your favorite song will end someday, which somehow makes you dance harder now. If this made you curious or a little poetic, stick around. We'll explore hopeful possibilities next time, how clever life might stretch the cosmic party, what strange corners physics leaves open, and even some wild ideas that sound like science fiction but are fun to imagine. If you enjoyed the trip, like, subscribe, and tell us which future scenario you want to see explored. Your questions shape the next video, so don't be shy, ask away.